OCPJP6 exam is 150 minutes duration. Total number of questions that you need to solve in it is 60 and passing score is 61%. Okay. And for this exam, the book that we recommend is SCJP6 Study Guide by Kathy Soya and Bert Bates. This is a very popular book. You can just Google it and the first result will actually get you to this book. You can in fact even buy this book from the Whizlabs store as well. I think Raj will probably share the details towards the end of webinar as well. And on the basis of the book, the whole syllabus can be actually divided into these 7 sections as you can see here. Okay. And if you want to see which section is covered on which day in our training, you can see that on this slide. Okay, so this slide actually lists down the detailed schedule of all the days. So for example, you can see which are the topics that are covered on day 1, day 2, day 3 and on day 4. Before I do that and begin on the technical topic for today, which is related to threads and concurrency, if anyone has any questions, please feel free to ask them. You can ask your questions through the questions panel here, or if you want to speak up, just let me know and I will unmute you. Alejandro, I can see one comment from you that you cannot hear me properly. I think it was written some times back, so I hope you are able to hear me clearly now. Okay, I don't see any questions anymore, so let me begin with the topic that we wanted to start today. Okay, so today I will give you an overview of threads and concurrency in Java. We will discuss a little bit about life cycle of threads in Java, then we will see the problem of synchronization in action with an example, and then towards the end of today's session we will have a quiz question in which we will just review whatever we have discussed and learned over the last 30 minutes. Of the technical discussion. Okay, so let me begin. So whenever you create a thread in Java, right, and by the time that you start it, it goes through various phases of the life cycle. Okay, so here are the life cycles of a thread which it needs to go through once you have created a thread object and once after you have started it. Okay, so the first state which a thread enters in is called the new state. Okay, new state is actually a very simple state. It is a state in which a thread enters as soon as you have created an object of it. Right, so as soon as you have created an object of a thread but haven't done anything with it like starting it, right, it is said to be in the new state. I can show you an example of that. This is the example that we will be actually discussing very shortly as well, but you can see that it has a class called withdrawer which is actually extending from thread, right? So basically this is our own thread that we have created. Now once you have created this withdrawer object here, right, now you can say that the withdrawer thread has entered the new state. New state is basically meaningless, you can say, right, because you never know when the thread will be actually started. Unless you start the thread by doing like this, by calling the start method on it, no new thread environment will be created, and hence, you know, new state is just basically meaningless. It's just a name given to the state when a thread enters as soon as you have an object of it. That's it, nothing more. Now, once you call the start method on a thread object, like you can see that I'm calling the start method here, right? So once you call the start method on a thread object, the state that it enters in is called runnable. Okay, runnable basically means ready to run. It's ready to run but not yet running. Why it is not running? It is not running because it is the job of something called a thread scheduler. So there is a component inside the JVM called thread scheduler whose responsibility is to decide which thread out of the ones that are present in the runnable state. So there can be multiple threads in the runnable state. Okay, you can imagine that in this example I am just calling start on one thread, right? But I could have created more withdrawer objects like this and called start on all of them, right? So if you do that, you will be creating multiple threads, right? And all of those threads, as soon as you call start, will go into the runnable state. Okay, now ultimately the goal of a thread is to execute its run method. Right? Whatever functionality you want the thread to execute, you need to provide it in its run method. right? So for example, like this, I have provided a very simple for loop which is doing some withdrawal from a particular account, right? So this is the functionality that this thread is supposed to execute. Now I provided it in the run method. Now it will not execute this run method until it enters another state called running. Okay. Now there can be only one thread in the running state, and it is the job of the thread scheduler to decide which thread out of the ones that are present in runnable state should go into the running state. So for example, let's say there are 3 threads in the runnable state, T1, T2 and T3. Now thread scheduler can decide any of these threads. It can pick up any of these threads to go into the running state. You don't have any control over that. You cannot control the thread scheduler's behavior to decide, let's say for example, pick T2 at this point of time. You cannot do that. Okay. And so for example, let's say thread scheduler picks up T2. Okay. Now T2 is running, right? T2 has entered the running state, which basically means it is executing its run method. Okay, it's executing its run method. Eugene, there can be concurrent execution. It depends upon how many cores or how many processors you are having in the system. For SCJP, you just need to be concerned with single processor environment in which there can be only one thread in the running state. Okay, so here we will consider the example in which only one thread is actually in the running state. Otherwise, of course, if you have multiple cores, multiple processors, and of course there can be multiple threads running concurrently, right? But for SCJP, you just need to be concerned about one thread in the running state. And again, it is solely the responsibility of the thread scheduler to decide which thread will be in the running state. Now, while a thread is in the running state, it will of course execute its run method, right? Now, while executing its run method, right? While it is executing its run method, thread scheduler can decide at any point of time that, okay, this thread has run enough and some other thread should be given a chance. So for example, it can happen that thread scheduler decides that, okay, maybe T3 should be given a chance now. So it will pick up T3 to go into the running state and it will send T2 back to the runnable state. Now when T2 is sent back to the runnable state, right, please remember when T2 is sent back to the runnable state, its local state is saved. Local state meaning whatever state the run method was in, right? Because it would have left run method in between, right? So for example, it would have executed, let's say, this for loop 3 times, right? When thread scheduler decides that, okay, this should be sent back to the runnable. So the state will be saved, right? Meaning, for example, the value of this I variable will be state that I was 3 or something like that. Whatever will actually provide the information back to the JVM when it comes back, that from where to actually start the execution. Okay, so here, for example, when T2 is sent back, its state will be saved. Okay, and whenever T2 is brought back into the running state, right, it can be brought back again, right, because it has not still yet finished its run method. So whenever it's brought back into the running state, it will resume its operation rather than restarting it. It will resume from wherever it left. And you can see eventually, because of this, a thread will actually finish its run method, right? Even though, let's say, by getting multiple turns at in the running state, right? So ultimately, it will finish its run method, and once it has finished its run method, it goes into a state called dead. So, for example, if T2 finishes its run method, it will ultimately go into the state called dead. This will be the eventual fate of all the threads. Eugene's question is, what is atomicity? So Eugene, by atomicity we mean basically that there are certain primitive variables like integer and double and boolean for which if you want to do some modifications to them, you can actually use their atomic form. If you do not use their atomic form, the modification operation that you are doing on them is not concurrent. So Eugene, you can elaborate your question further, because that's what I understood from your question. Please go ahead and You mean interrupting a thread? Yes, Eugene, I can unmute you. Just give me a minute. All right, Eugene, I have unmuted you. Go ahead.
Okay. Can you hear me?
Yes, I can.
Okay. I'm sorry. Atomicity has special meaning in threads, and I used it out of context. I will use other words.
Sure, yeah.
Okay. We're talking about thread scheduler.
Right.
Okay. What is the unit of work that it will not interrupt?
Okay, unit of work that it, yeah, I can give you, so you need to be very careful.
No, I mean the smallest unit of work. Not if I will protect the something, but if when you want to go from one thread to another thread, he can stop any time whatsoever in the middle of anything, or it needs at least to finish some small operation. And if it's so, what are the smallest operation it needs to finish?
Yes,
That's my question.
Right. So it actually depends upon what exactly you are trying to do. For example, if you are trying to assign something to an object reference variable, that is considered to be an atomic operation. It will not be interrupted in between. So I can give you, for example, this is not an atomic operation. Int balance equal to 390, which we are doing here. This is this is actually outside the method. Let's say if it was inside something like this, this is actually not an atomic operation, and it can be interrupted in between. So ideally, if you are putting synchronized block, for example, you should put this complete thing inside it. But if you are trying to do something like this, let's say we have something like this, object obj equal to new object, right? Or basically any object reference, I mean. This object I've just used in general so that it applies to any object reference that you have, okay? This is considered to be an atomic operation. So it will not be interrupted in between, that this obj will either be assigned to it or it will not be assigned to this whatever address this object is. It will not be in an intermediate state.
But loops will be interrupted.
Yes, of course.
Thank you.
Okay, I can see few more questions. So Eugene, I'm muting you. You can ask me to unmute you whenever you have any further question, okay?
Yes, please, mute me again.
Thank you. Okay, I can see 3 questions, so I will start with the question from Arjun. Arjun is saying how the states are changed, like running to runnable and runnable to running. So Arjun, that totally depends upon the thread scheduler, right? So for example, if a thread is in the running state and thread scheduler decides to put it back into the runnable state so that some other thread can be given a chance, right? It actually switches from running to runnable. Again, that depends upon what is the scheduling algorithm that is present inside the thread scheduler, and that can of course change from JVM to JVM. And as a Java developer, you should not be actually worried about that. Right? So I'm not sure if your question is actually regarding the thread scheduling algorithm, that when it will decide which thread to send from running to runnable and vice versa, or you just mean that how are states being changed here? Then Alejandro's question is how a thread passes from running to runnable instead dead after finishes run method. So Alejandro, that can actually happen, right? Dead state basically means that the thread is finished. It has finished its run method, right? Running means it is still executing its run method, right? And runnable means it is ready to run and it has not finished its execution yet. Okay, I think next question is in the code how account object is created in the withdraw thread. Okay, so Leandro, you can see this code here. I'm not creating account object in the withdrawal thread. You can do that if you want, but here you can see I created an account object and then I'm associating this account object with this withdraw, right, through this instance variable here. Okay. Yeah, yes, Eugene, I can preserve this notepad, and I think we can share this with all the participants. Suresh, question is, can thread goes from running state to runnable? Suresh, yes, it can go from running to runnable, and that is why we actually have the problem of synchronization, because a thread can switch from running to runnable and runnable to running at any point of time. Sukumar's question is, can we control the thread scheduler by the program? So Sukumar, no, you cannot control the thread scheduler explicitly. However, there are few APIs available in threads, like there is an API called sleep, right? So as soon as you call sleep, the current thread which is currently in the running state will immediately go into the sleep state. So you can say that you have influenced the thread scheduler behavior a little bit, right? Because you have sent the currently running thread into the sleep state, right? And now the thread scheduler will need to pick up a new thread, right? There are certain other APIs like yield and join, etc. But of course, they will take much longer time if we start discussing about them. So there are certain ways in which you can influence the thread scheduler's behavior, but I won't say that you can explicitly control the thread scheduler's behavior. Okay guys, let me actually move forward. Gothman, regarding thread local, again, it's a very broad topic, and I'm afraid I will not be able to cover it here, because otherwise we will miss what I actually wanted to cover here today. Okay, we will not be able to even touch synchronization and other issues. So let's finish whatever we are actually discussing right now, and in the end, if we have time, we can of course discuss all those things as well. Eugene, yes, you can actually give priorities to thread. There is something called set priority API available, but again, don't rely too much on it. Because if you will see in the JVM specification, it's clearly mentioned that you should not rely on setting the priorities of the thread and expecting that those threads will be actually really given very high priority by the thread scheduler. Okay. So you can use them if you want, just like you have that garbage collection API, you can use that if you want, but don't rely on it, because it may or it may not actually work, depending upon which JVM you are actually running on. Okay, so with this, let's come here and let's see this example of account tester that I'm having. Okay, so in this you can see I have an account class, okay, which has a property called balance. Right, and there is a withdraw method that I have provided here, right, which is doing what? It is first of all doing a diff by calculating the difference between balance and amount, checking whether balance is greater than diff is greater than 0 or not, and if it is greater than 0, then basically deducting the amount from balance. And now here I have the withdraw thread, which is inside its run method. Okay, I can remove this line from here. Inside its run method, it is doing what? It is just trying to do 5 withdrawals of 100 units each. Please note, it is trying to do 5 withdrawals of 100 units. Okay, and the account is initialized with an amount of 390. Okay, so my question is, let's say if you run this code multiple times, maybe 1,000 times, or how many times you want to execute it, will there ever be a situation in which balance becomes negative? Can it happen ever that you see this balance as negative? So people who are thinking that it will be negative because I am doing 5 withdrawals here, please note that I do have this check here. Right, so after the third withdrawal, or after the third withdrawal, when we come to the 4th iteration, this diff will be less than 0, and we will not deduct balance from, amount from balance, right? So that way, straightforward, it will obviously not become negative, because we do have a check here, right? But is there any other way through which it can actually become negative? So guys, right now we have just one thread. So my question is regarding just one thread in the system. I will add another thread once we are clear about this. So, but right now, assuming that there is only one thread according to this code, as you can as well see. So anyone thinking that this balance can become negative? Alright, so answer is basically no. If we leave the code as it is, you will never end up in a situation in which balance becomes negative. Okay, because we just have one withdrawal, there is no other thread competing with it on the on deducting this amount from balance, right, in the account object. So you will never end up in a situation in which this balance becomes negative. Okay, now let me do some changes here. Okay, what about now? Now I have created another withdrawal and I have given it the same account object. Can balance become negative now, or will it always become negative? Alright, so guys, answer to the question here is that it can actually become negative. Let me actually show you how it can actually become negative. Right? It is not guaranteed that it will always become negative, but it depends upon what are the decisions that the thread scheduler actually takes while scheduling these two threads. Okay, so in certain cases it can become negative. So let me show you one of those cases. So what are we having here? Let me just put it here. Oh, maybe let me open the new one. Okay, so what are we having here? We are having two threads here, right? W1 and W2, right? So let me just write down the states that a thread can enter in. Okay, so we have this runnable state. We also have this state called running. Okay, and we have just one common account object on which both of these threads are operating, right? So I will just create a section called heap in which that account object is there, right? So let's say the account object is created at some location in heap, and we have that balance property there. Balance property which is 390 initially. Okay, so as soon as you call start on the withdrawal threads, what happens? Both of them actually comes to the runnable state. Okay, now let's say thread scheduler decides that W1 should run. So W1 comes into the running state. Okay, now when W1 is running, okay, now when W1 is running, what will happen? It will check its for loop. Inside the for loop, the first iteration is asking it to withdraw 100 units from the account, right? So what will happen? It will go to this withdraw method. It will see diff will come out to be 390 minus 100, which is 290. It is greater than 0, so it will go inside this if condition, deduct the 100 unit from balance, and balance will become 290. Okay, please note that it was not interrupted by thread scheduler during this iteration at all. Let's say it is allowed to execute its second iteration of the for loop as well. Okay, if it is allowed to execute its second iteration of the for loop, the balance will become 190 after that. Okay, now let's look at the third iteration very carefully. Okay, Now while executing this third time, what is going to happen? It will calculate diff. Diff will come out to be, what will be the value of diff in this next iteration that we are executing? $90, right? So I will write down that diff is 90, right? And diff is greater than 0, so we will go inside this if condition, right? Now this condition has been checked, right? So the line that is supposed to be executed next is this, balance minus equal to amount. But before it can execute this line, let's say the thread scheduler decides that it has run enough and W2 should be given a chance now. So it is sent back into the runnable state, right? State is saved. You can see diff is 90. So this, all this state information is there with it, so that when it comes back, it can actually resume it from there. Let's say now W2 is brought. So W2 comes and W2 executes for the first time its run method, and it goes for its first iteration, and let's say it is allowed to execute its first iteration without any interruption. So balance will become 90, right? Balance becomes 90 after that, after the first iteration, right? Now let's say after the first iteration of W2, right, W2 is sent back to the runnable state by the thread scheduler. So W2 goes back into the runnable state and W1 is brought back, right? For some reason W1 is brought back. Now W1 will of course not start afresh. It will only start the execution from wherever it was paused or wherever it was sent back to the runnable state, and it will remember that it has to start the execution from this line, right? Now if it executes this line, what will be the value of balance after this? -10, right? So after this, so it will immediately execute this line because it had already done the if check, so balance will become -10. Okay? So is this clear to everyone, first of all, that how balance can actually become negative in this scenario? This is actually the problem of synchronization, which we are actually going to solve now. Okay, great. I can see, because this problem should be very clear, otherwise understanding synchronization will not make much sense, right? Because first of all, problems should be clear and then only solution will make much sense. Okay, so we all can see the problem now. Now how to solve this? You can actually solve this using something called synchronized block in Java. I will explain you about how the synchronized block actually works. Let me just write it down first of all. What you need to do at a very high level point of view is whatever critical code is there, so this all is the critical code here, you need to wrap it inside something called synchronized block in Java. How will you do that? You will first of all write synchronized keyword. Okay, the synchronized block takes an object reference as the parameter, you can say. It's actually not a parameter, it is something on which a lock can be obtained. So you must provide an object reference here, which is pointing to some object, pointing to some valid object in heap, right? So for example, in this scenario, I can just say this, because we are anyways executing this withdraw object on the account object, right? So why unnecessarily create another object and obtain a lock on that, when we can actually do create the lock on the account object itself, right? So I will say synchronize this, and I will just put all of this code inside the synchronized block. Now how this synchronized block actually works? Okay, so for that, let's come to this heap here, right? So every object in Java has something called a lock associated with it. Okay, so there is something called a lock associated with each and every object that is there, right? So you can see, imagine that this heap will have a lot of other objects as well, right? At different locations, can be account object, student object, employee object, string object, or whatever objects you can actually have, right? All these objects have something called a lock associated with them, and this lock can be occupied by only one thread at a time. Okay, this can be occupied by only one thread at a time, and if a thread has occupied a lock, then no other thread can occupy that lock until the thread which has occupied that lock releases it. So for example, imagine that this account object is already locked by a thread called T1, right, and suddenly thread T2 comes, right, and it also tries to obtain a lock on this account object. It will see that this lock is already obtained by T1, right? It will see that T2 will see it has to occupy a lock on 1000x location in heap, right, which is an account object, but the lock is already there with T1. So what it will do, it will just wait for T1 to release that lock. Until T1 releases this lock, T2 cannot obtain a lock on it, and hence T2 will just wait there. Right? This is what we actually do when we actually write the synchronized block. What this synchronized block does is that it makes sure that a thread will only enter inside it only after getting a lock where this reference is pointing to. Okay, please remember, we are not obtaining a lock on the reference. We are obtaining a lock on where reference is pointing to, right? That is the address in the heap, not on the reference. Reference can change the objects again and again, right? But the synchronized block will be locked on the object that this reference is pointing at this point of time. Anyways, that will become more clear once I change this reference to something else. Okay, now let's see how this will actually prevent balance from becoming negative, right? We have actually seen this, but how is it actually preventing balance from becoming negative? So let's see that. Okay, now again we will just iterate through the same problem. We will go through the exactly same scenario that we had earlier, and we will see if balance can still become negative. Okay, so I'll just remove all these things from here. Don't need this. And by the way, if anyone has any questions so far, please let me know. Lock is empty on the account object. There is no lock right now. Balance is 390, and okay, we can actually remove this, and both of the threads are in the runnable state. Okay, now let W1 comes into the running state like earlier. During its first iteration, W1 first of all needs to occupy a lock on the account object, right? Because this will be pointing to 1000x location where the account object is. So it will occupy a lock here. It will execute its first iteration where the balance will become 290. Eugene, I will come to the synchronized method. Don't worry. If you understand this concept of synchronized block, then synchronized method is actually nothing new. It is just a shorthand of writing this synchronized block like this. There's nothing new in when you actually do synchronized methods. Okay. Now, during, of course, when the synchronized, it has executed all these things and it comes out of the synchronized block, W1 will of course release this lock as well, right? Now it comes for the second iteration because of the for loop, and during second iteration again it occupies a lock. It changes balance to 190, right? And again it releases a lock, right? Because synchronized block is finished for that iteration. Now, when it comes for the third iteration, right, again it occupies the lock, right? Lock is with W1. Now it calculates the diff. Diff will come out to be 90, just like earlier, right? And we do this check if the if check as well. Diff is greater than 0, so we are just about to execute this line in W1, balance minus equal to amount. But before it can do that, let's say the thread scheduler decides to send it back, just like it happened earlier, right? It is sent back. Now at this point of time, W2 is picked up to run, so W2 comes. Now when W2 enters inside its run method, it sees that it has to do a withdraw from the account object. So it comes here and it notices that inside the withdraw method there is a synchronize statement, and because of that it has to first of all obtain a lock on the account object in order to proceed ahead, right? And it goes to the location where this is pointing to 1000x, and it sees that the lock is still with W1. lock is still with W1, so it will just wait here because it cannot obtain that lock until this lock is released by W1. So it will just wait here. Eventually thread scheduler will see that W2 is doing nothing rather than just waiting for the lock to be released. So it will be sent back, right? Of course it will be sent back after some time, right? W1 will be brought back. W1 is brought back. It will execute this balance minus equal to amount. Balance will become 90. Okay. And after that, it will now release the lock because synchronized block is finished. Lock is released, right? And after this, now if W2 comes, it can occupy the lock, but you can see the balance will not become negative anymore, right? Because it is already less than 100 and this if check will prevent it from becoming negative now. Okay, I can see a few questions here now. So Eugene's question is, what process actually does locking and unlocking? So it's actually done at this point of time, right? As soon as you enter inside the synchronized block, the lock is obtained on the object on which you are trying to do a synchronization on, and the lock is released at this point of time, right? And Eugene, the last part of your question, what if a thread is killed by a user before the lock is released? Right, that is actually an ambiguous situation, and that is why you are actually not advised to kill a thread. There used to be an API called thread.suspend, but it has been deprecated, I think, long time back, precisely because of one of these reasons. You're actually not advised to actually kill a thread or suspend a thread yourself because of these situations, because it could have obtained a lock on some objects, and what will happen to that? Because that lock will never be released, right? So because of these things, you are actually not supposed to use the APIs like thread.suspend. There you can anyway see in the Java doc, they will be marked with heavy warning that you should not be using them anymore. So Eugene, when user forcibly closes a window, in that case the thread will actually exit gracefully in that case. Okay, it will depend upon what kind of thread you are actually having. So for example, if you have a UI thread, it will have a handle for the close call that is actually being made, right? The close command that is being sent or the close event that is being there, you need to actually handle that. That's mostly in the UI programming, you will see those kind of things. Okay, I can see one question from Hardik and Alejandro. How thread scheduler is useful in this case if you can use synchronized block? So Alejandro, thread scheduler is something internal to JVM, and it is useful, right? Because it is actually scheduling or scheduling the threads and giving them a chance to actually run, right? Without thread scheduler, you will have to do that yourself. Right, you will have to schedule your threads yourself, which thread should run at what point of time. So thread scheduler is anyways useful, but synchronization is something you need when you are trying to use different threads on same object, or you are trying to modify the state of an object through different threads, right? In that case, you actually need something called synchronization. So synchronization and thread scheduler are not competing with each other. So you cannot say that if you have synchronized block, you don't need thread scheduler, or if you have thread scheduler, you don't need synchronized block. Both complement each other, you can say. Okay, Hardik is asking about the deadlock scenario. So Hardik, yes, I can actually give you an example of deadlock scenario. In this case, the deadlock will not happen, Hardik. Okay. In this scenario, deadlock is not going to happen. I can actually show you when a deadlock can actually happen. So deadlock normally happens when you are trying to obtain, when you have nested synchronizations. Okay. So let's say we have a method called M1 defined somewhere. let's say you have this class test and it has object obj1 and object obj2, right, and both are initialized, so something. Now in M1 method what you are doing is following. You are saying synchronized obj1, okay, and after that, once you have obtained a lock on the location where obj1 is pointing to, you immediately try to obtain another lock, right? You can do that, and you try to obtain a lock where obj2 is pointing to, right? And once you have obtained both of these locks, you do something, right? So you have any code that you want to actually run here, right? Any code that you want to run. Now we have another method here, let's say called M2, in which what you do is you again do a nested synchronization like this, but in a reverse manner. You first try to obtain a lock on obj2 and then you try to obtain a lock on obj1, right? Now this is a scenario in which deadlock is quite common. Deadlock can actually happen. It has a very high chance of happening in this scenario if what you do is in a thread you call M1 method and in another thread you call M2 method. Of course on the same test object. So let's say there is a single test object and one thread calls M1 method on it and another thread calls M2 method on it, right? Can anyone see the deadlock here? The deadlock should be quite evident, right? You can see that let's say the thread T1 is executing M1 and thread T2 is executing M2, okay? And let's say here is what happens. T1 enters inside the M1 method and it occupies a lock where obj1 is pointing to, okay? So you can say that obj1 wherever it is pointing to, T1 is occupying a lock on it. Okay, T1 has occupied a lock on it. Now immediately at this point of time, right, as soon as T1 has occupied a lock on this obj1, let's say it is sent back to the runnable state and T2 is brought, which is starting its execution of M2. T2 sees that it has to occupy a lock on obj2, right? obj2 is empty right now, nobody is occupying that lock, you can see, right, wherever obj2 is pointing to. So T2 gets that lock without any issues, okay? And after that T2 tries to obtain a lock on obj1, but who is obtaining is obj1 free? No, obj1, the location where obj1 is pointing to, the lock is already with T1, right? So T2 cannot proceed further, right, because it is waiting for lock on obj1 to be released. So eventually thread scheduler will decide to bring back T1. Can T1 proceed? No, because T1 was interrupted at this line, and in order to execute this line it has to obtain a lock on obj2, right? Sorry, location where obj2 is pointing to, not on obj2, and obj2 is pointing to some location in the heap where this object is, but this lock is with T2, right? So T1 also cannot proceed. T1 is waiting for T2 to release the lock and T2 is waiting for T1 to release the lock. Okay, so you can see none of them can actually proceed ahead, and this can actually lead to deadlock. Is this deadlock clear to everyone? Alright, great. Okay, so guys, just one quick question that I actually wanted to discuss. We are actually running out of time, but I think we might have just enough time to actually just cover up this question. Okay, so you can quickly see this question. It's a very simple question. You have this class called store, in which I have this method called fetch, right? And I have two system.out.println. One is printing ID and another is printing ID plus 1, right? Just incrementing it by 1 and printing it. Then I have a class called fetcher, which is nothing but a thread and operating on a store. It is given an identifier, right? And what it does is that when the run method is called on it, it calls the fetch method of store with a particular ID, right? Whatever ID you supplied. And you can see we are creating a store, then we are creating two fetchers. We are giving same store object to both of the fetchers. One fetcher is given the ID 0, so it should actually print 0 and 1. Right, whenever it is run independently, let's say it will print 0 and 1, and this should print 6 and 7. Right? So my question is, what can be the output when you actually run this code? So let me give you a few options, okay? Because otherwise it can be a bit confusing. So let me give you a few options regarding what can be the output here, okay? So maybe I can write it down on the notepad. Yes, Srinath, we will actually send you this presentation and this whole recording as well. Don't worry about that. Okay, out of these 4 outputs, so this is the first output, this is the second output, this is the third output, and this is the fourth output. Do you think all those 4 outputs are possible, or any of the output is not possible? Okay, great. So I can see that people have answered it correctly, that the first 3 outputs are possible, last one is not. Last one is not possible because 1 cannot be printed before 0, right? 1 cannot be printed before 0, it will always come after 0. And the first 3 are possible in the following manner. 0167 denotes that the thread with the F1 was not interrupted, and after that F2 occurs, F2 runs. So this is by running F1, and this is by running F2. In this second output, first F2 runs and then F1, and in the third one, first F1 runs, after that it is interrupted and it is sent back to the runnable state, and F2 runs. F2 is sent back and F1 is brought back, because of this 1 gets printed, and finally F2 is brought back, so 7 gets printed. Okay, now let me just quickly change this to a synchronized method. This is actually what kind of is the kind of question that you can get in exam from this particular topic. Okay, so okay, any changes in your options now? The last one is of course not possible, so I will just remove it. Yes, of course. The first 2 are possible, the last one is not possible. So you will never see a mix and match between 2 threads running, right? If a thread executes its run method, it will finish it, because this fetch method you can see is synchronized, right? So once a thread has entered inside the fetch method, it will actually print out its both ID values, ID and ID plus 1, before getting interrupted by any other thread, right? Because it will obtain a lock on store, and no other thread can actually enter inside the store's fetch method until the first thread releases the lock. So yeah, the first 2 outputs are possible, the last one is not. Okay, great. So guys, I think I'm actually running out of time, so I will wait for the questions here, and meanwhile I will hand over the access to Raj. So Raj, you can actually take over.